Hi guys, so today we'll be solving questions from NCERT class 12 maths chapter 1 relations and functions, and we'll be looking at the first exercise 1.1. Here's the first question. Determine whether each of the following relations are reflexive, symmetric and transitive. Right, so before we go ahead and solve the questions, let's refresh our understanding of what we mean by a reflexive relation. A reflexive relation, what we mean by a symmetric relation, and what we mean by a transitive relation. Right? Reflexive is where every element is related to itself. Okay? And a symmetric relation is where you should be able to interchange any pair of given numbers. So if you have a pair x comma y in the given relation, then you should be able to interchange and still be able to satisfy the given relation. Y comma x should also be able to satisfy the given relation. That's why it's called a symmetric relation, right? And a transitive relation is where if you have three elements, let's say x, y, and z, if you know that x comma y is a valid relation and you know y comma z is a valid relation, then x comma z should also be a valid relation in that given set. So then you can say that the relation is transitive, right? So in this case, if you have any two, let's say you have two numbers in the set x and y, you should be able to say that you should be able to replace y with x and still get the same answer. So for example, in this case, in the set, you have a set 1, 2, 3 all the way up to 13 and 14 defined as R is a set such that, so this means such that, right? So R is a relation such that x in the set A, R relation in the set A is defined as R is x comma y such that 3x minus y is 0. So if it has to be reflexive, what do you need? You need to be able to replace y with x and still get the same answer. That's the whole idea of it being reflexive, right? So if you say 3x minus x is 0, you get 2x equals 0. So is this valid for all these values? 2 into 1 is not 0. None of it is valid, right? So if it is not valid, that means it is not a reflexive set. In any reflexive set, you should be able to replace a number with another number in that same set and still the relation should be valid. So this is not valid, it's not reflexive. Now, if the relation has to be symmetric, what do you need? The relation needs to be symmetric. You need to be able to interchange the given variables and still be ending up with a valid relation, right? So in this case, we are told that 3x minus y is 0. So that means 3x equals y, which means y equals, or which means x equals y by 3, correct? Which means x equals y by 3. Which means x equals y by 3. So if this has to be valid, all the numbers here are integers, right? So if this has to be valid, then that means y has to be a multiple of 3, right? Only then this can work. But if you interchange the two values, so you're going to get 3y minus x is 0, right? So which means x will now be a multiple of 3. So x has to be a multiple of 3 in this case, right? Which means x by 3 is y. If x is not a multiple of 3, you're not going to get y to be an integer. So now in this case, y would be either 3 or 9 or 6 or 12, right? But what if y is 12? X has to be 36, right? X has to be 12 times 3, which is not valid. So that means you cannot interchange and still have a valid relation here. So this relation cannot be symmetric, right? Now, what about transitive? So transitive means you should be able to have, if you have three values, x, if you take three numbers, you take 1, 2 and 3. If you have 1 and 2 working in the relation, you will have, if you have 2 and 3 working in the relation, you will still have 1 and 3 also working in the valid relation. Will that be the case? So to prove that, what you could do is, you could see, you could take, if you take 3x minus y is 0 and you take 3y minus z is 0, right? What do you get here? You get x equals y by 3, correct? And you get y equals z by 3, which means x would be equal to, so if you replace y here, so it would be z by 3 by 3, it's z by 9. So which means 9x minus z is 0. Actually, I should have taken more space for these questions. Okay, anyway, I'm going to be taking it below this. So which means 9x minus z is 0, right? Which does not satisfy the original relation, right? So see here, you need to have the, if it is a transitive relation, then if this is true and this is true, you also need to say 3x minus z is 0. That's the whole point of having a transitive relation, right? So if x and y are put in that same value and y and z are put in the same value, then x and z would also need to be in the same value. But if you add in these two, you're going to get 9x minus z is 0, which does not satisfy 3x minus z. So this is not transitive either. So it is neither reflexive, neither symmetric, neither transitive. All three don't apply to this relation. I know it's a lot, but let's keep going. Let's take the second one. So I'm going to take this one, right? Relation R in the set of n of natural numbers defined as R is x comma y such that y equals x plus 5 and x is less than 4. So in the set n of natural numbers, okay, so that is the overall set, and we have a relation defined in this way. Now let's see if it is reflexive. Is it reflexive? Is it reflexive? Now what do we mean by reflexive? So every element needs to be related to itself, right? So that means when you have a relation y equals x plus 5, every element needs to be related to itself. That means you should be able to replace y with x and should still be valid. X equals x plus 5. Is that valid for a set of n of natural numbers where x is less than 4? Obviously not, right? So you cannot have 1 equals 1 plus 5 or 2 equals 2 plus 5. It's just not possible, right? Any natural number will not be equal to itself plus 5. Just not happening, right? So it is not reflexive. It is not reflexive. Is it symmetric? Is it symmetric? So what do we mean by symmetric? You should be able to interchange these values and still have a valid relation, right? So you have y equals x plus 5, which means you should be able to interchange this and still have a valid relation, which means you will say x equals y plus 5 should also be valid. Is that valid? So let's take a couple of examples. If x is less than 4, right? So let's say x is 1. So then y would be 6, right? So if x is less than 1, you will have 6 equals 1 plus 5, right? So if x is 1 and y is 6. So if x is 1 equal to 6 plus 5? No, it's not. So it's not symmetric. Even one counter example is enough for you to prove that this is not a symmetric relation. Every single element needs to be able to validate that particular relation, and only then you can say it's symmetric, right? So is it transitive? Is it transitive? Now what does transitive mean? It means that if you have two elements, let's say you have x comma y and y comma z are valid, and x comma z would also be valid. So if you take x as, let's say, 1, then y would be 6, right? If you take x as 1, then y would be 6, right? So if you have x as 1, you have y would be 6 in the relation. If you say y is 6, what is z? So if you have z equals y plus 5, right? So if z equals y plus 5, then z would be 11. So does that mean z equals x plus 5? No. So z would not be equal to x plus 5, which is supposed to happen if it is a transitive relation. But it's not transitive, so this is not valid. It's not transitive because this relationship does not hold, right? So it's not reflexive, not symmetric, and not transitive. Okay, let's go to the third question. Relation R in the set of 1, 2, 3, 4, 5, 6 as R is equal to x comma y such that y is divisible by x, right? So is it reflexive? Is it symmetric? Is it transitive? Let's check. Now reflexive means every element is related to itself. Is it reflexive? This is an interesting question, because if you say y is divisible by x, then if it's reflexive, you would say, is x divisible by x? Remember, you just need to replace this with the same value. If y is divisible by x, y is divisible by x, is x divisible by x? X is divisible by x, right? So every element is related to itself in this case. You will always have a number being divisible by its own self, right? So this is reflexive. That's true. Is it symmetric? If y is divisible by x, does it follow that x is divisible by y? Obviously not. 100% it's not true. If any number is divisible by some other number, the opposite will never be true, because that number will be much higher than the other number or equal to the other number, and it's rarely true, right? So it's only possible when the numbers are the same, right? So only in one case it's true, and most of the other cases it's not going to be true. So if you say 4 is divisible by 2, 4 is divisible by 2, but does that mean 2 is divisible by 4? No. So most of the time it's not going to be true. This is not symmetric. Now, is it transitive? So if you say y is divisible by x, y is divisible by x, and you say z is divisible by y, do you think z will be divisible by x? Yes. Because if you have a number where you say 3 is divisible by 1 and 6 is divisible by 3, is 6 divisible by 1? Yes. Because if a number is a factor of another number and another number is factor of that same number, then you'll always have that smaller number being a factor of the bigger number. So this number will always be a factor of this number, because if it divides this number equally, then if that number divides the other number equally, then the smaller number will always divide this number in an integer format, right? So that means this is transitive, right? Next, go to the next question. Relation R in the set Z of all integers defined as R is x comma y such that x minus y is an integer. Again, is it reflexive? Is it symmetric? Is it transitive? Let's check. Reflexive means every number is related to itself, right? X minus y is an integer. So x minus x will always be an integer, right? So x minus x is 0. X minus x is 0, so it will be 0 is an integer and it will always be an integer. So it is reflexive. Is it symmetric? If x minus y is an integer, will y minus x be an integer? 100% yes. If x minus y is an integer, if x minus y belongs to I, y minus x will always belong to I. It will always belong to I. So it is symmetric, yes. What about transitive? If x minus y is an integer and y minus z is an integer, is x minus z also an integer? Yes, 100%, right? If x minus y belongs to I and y minus z belongs to I, x minus z will always belong to I. It will be a set of integers. So this is also true. Great. So first time we have something which is true in all three cases. Relation R in the set A of human beings in a town at a particular time is given by R is equal to x comma y such that x and y work at the same place. We have 5 different questions here, but quickly let's do it. So reflexive, symmetric, transitive. Reflexive, symmetric, transitive. Reflexive, symmetric, transitive. Reflexive, symmetric, transitive. Reflexive, symmetric, and transitive. Let's just mentally do this. So x and y work at the same place. Does that mean x works at the same place as x? Obviously, right? So if a person can only work at the same place as himself, right? That's true. It is reflexive. Is it symmetric? If x and y work at the same place, will y and x work at the same place? Obviously. And if x and y work at the same place and y and z work at the same place, do x and z work at the same place? Obviously. It's true in all cases. Now, if x and y live in the same locality, pretty much the same thing as the same place, right? So if two people live in the same locality, and you obviously know that if a person lives in the same locality, will he always live in the same locality? Yes. If x and y live in the same locality, does x live in the same locality as x? Obviously. It is reflexive. Is it symmetric? X and y live in the same locality, y and x live in the same locality. Symmetric. Transitive. X and y live in the same locality, y and z live in the same locality. Do x and z live in the same locality? Obviously, yes. Right, now x is exactly 7 centimeters taller than y. Now, if x is exactly 7 centimeters taller than y, can x be exactly 7 centimeters taller than x? Obviously not. You cannot be taller than yourself. If x is taller than y, is y taller than x? Obviously not. You both can't be taller at the same time. If x is taller than y and y is taller than z, can x be taller than z? No, can't be. It's not all three. Now, x is wife of y. If x is wife of y, can x be wife of themselves? No, cannot be. It's gonna be very weird, but okay. If x is wife of y and y is wife of, and can y be wife of x? No. If x is wife of y and y is wife of z, can x be wife of z? No. At least not morally. If x is by a father of y, can x be father of himself? No. If x is father of y and y is, can y be father of x? No. If x is father of y and y is father of z, can x be father of z? No. Can be a grandfather. So that's not true either. Great. So we finished the first set. Let's go to the next question. All right. Let's go to question number 2. Show that the relation R in the set R of real numbers defined as R equals in the set R of real numbers. It's in the set of real numbers defined as R equals a comma b, where such that a is less than equal to b square. This is b square. It's b square is neither reflexive nor symmetric nor transitive. Right. So the relation is a comma b such that a is less than equal to b square, right, on the set of real numbers. Great. So we want to check if it is reflexive, symmetric, or transitive. Right. So what do we do here? So reflexive is where every element is related to itself, right? So if a is less than equal to b square, will a be less than equal to a square? So will all numbers be either less than or equal to its square? Absolutely, right? It will always be the case. So any number you take will always be less than equal to its own square, right? So a minus 2 will always be, a square is always going to be positive. So any negative number will always be less than or equal to its own square. If it's a minus 1, it will be equal to. But if it's, sorry, even a minus 1 won't be equal to, right? So it's a positive number and it's a 1 or a 0, it will be equal to its own square. And every other number will always be less than its own square. So this works out. So it is reflexive. So this reflexive is true. Now let's see about transitive. So sorry, about symmetric. So as we spoke before, if a is less than equal to b square, for symmetry, you will need b is less than equal to a square, which can't be possible, right? If a is less than equal to b square, b is not necessarily less than equal to a square. It could be greater as well, right? If you take, for example, a is 1, if you take a is 1 and b is 2, so 1 is less than equal to 2 square. That's correct. But is 2 less than equal to 1 square? No. So this itself proves that this is not a symmetric function, right? And you could come up with more and more examples if you want. So is it transitive? If a is less than equal to b square and b is less than or equal to c square, does it mean a is less than equal to c square? Not necessarily. Right, let's say you have a is 2 and b is minus 2 and c is 1. So a would be less than equal to b square, which is 4. But b will be less than or equal to c square, which is 1. But a is 2 will not be less than equal to c square, which is 1. So this is an exception to this case. So it is not necessarily transitive. It is not transitive because even one exceptional case in the entire set will invalidate the entire relation, right? So it's not transitive. It is reflexive, not symmetric, and not transitive. Let's move to the next question. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R. So it is R is a comma b such that b is equal to a plus 1. Is reflexive, symmetric, or transitive again? So reflexive, symmetric, and transitive. Right? Let's go through each case as we always do. Every element will be related to itself. But is that true? Can you have a equals a plus 1 ever in the set of these integers? No, you can never have a number being equal to its own self plus 1 when you have all positive integers, right? So it's just not going to happen. So it is not reflexive. Can you have, if b equals a plus 1, can you have a equals b plus 1? No, because if you say 2 equals 1 plus 1, you cannot say 1 equals 2 plus 1, right? So that's not going to work. It cannot be a symmetric function. You cannot interchange the values and just still get the same answer. Not going to happen. Is it transitive? If you say b equals a plus 1 and you say c equals b plus 1, does that mean c equals a plus 1? No, absolutely not. So if you say this, you will say if c equals b plus 1, this means c equals a plus 2. And that's not the same as a plus 1, right? So this is also invalid. This is not transitive as well. So neither reflexive, nor symmetric, nor transitive. Great. Let's move to the next question. Show that the relation R in R is defined as R equals a comma b less than equal to b is reflexive transitive but not symmetric. Right. So the relation is in R, so all real numbers a comma b such that a is less than or equal to b on real numbers. Right? So okay, let's see if it is reflexive, symmetric, or transitive. It's the question is actually telling us that we need to show it is reflexive and transitive, so we know that it is reflexive. Yes. So if a number always less than equal to itself, 100%, right? A is always less than equal to a. It's 100% true. A number will always be equal to itself. So since it is less than or equal to, it's always equal to. Equal to is always true. So this is true. It's always reflexive. A number will always be equal to itself. It's true. Now, is it symmetric? If I have a is less than equal to b, does that mean b is less than equal to a? Not necessary. If a is less than equal to b, if it is equal, then you have this equality. But if it is greater, if b is greater than a, you cannot say b is less than a at the same time, right? So that's not true. You cannot have a number be greater and lesser at the same time. It could be equal though, but it cannot be less than or greater at the same time. So it's not symmetric. Now, is it transitive? If a is less than equal to b and b is less than equal to c, does that mean a is less than equal to c? Yes. If a is less than b or equal to b, let's take the case, right? So if a equals b, for example, if you take the first case, a equals b, right? And if you say b is less than or equal to c, if a equals b, a will always be less than or equal to c. And the second case is a is less than b, right? If a is less than b and b is less than or equal to c, a will definitely be less than or equal to c. It's less than. If b is less than c, a is obviously less than c, right? So a will be less than c in both these cases. Even if a is equal to b or is a is less than b. So a less than or equal to c holds true. So that's why this is transitive. Great. Let's move to the next one. Okay. The fifth question says, check whether the relation R in all real numbers is defined by R equals a comma b such that a is less than or equal to b cube. Is reflexive, symmetric, or transitive? Great. So let's follow the same drill: reflexive, symmetric, and transitive, right? So if it is reflexive, what do we know? We say every element is related to itself, right? So if is a less than or equal to a cube, the question is a less than or equal to a cube? It might seem like it is, but if you check for negative numbers, let's say for example minus 2, is minus 2 less than or equal to its own cube? Minus 8 is the cube of minus 2, right? So minus 8 is actually a number larger than minus 2. If you think about the number line, right? 0 is here and minus 8 is here, minus 2 is here. So minus 2 is actually smaller than minus 8 is actually smaller than minus 2. So in this case, minus 2 is actually greater than minus 8, and this does not hold true, right? So this means it's not reflexive. Is it symmetric? So if a is less than or equal to b cube, does that mean b is less than or equal to a cube? Can you think of any counter examples to this? So if you have 1 is less than 2 cube, does that mean 2 is less than 1 cube? No. Very simple, right? So 2 is not less than 1 cube. 1 is definitely less than 2 cube, but 2 is not less than 1 cube. So it is not symmetric. Right. So is it transitive? Is it transitive? If A is less than equal to B cube and B is less than equal to C cube, does that mean A is less than equal to C cube? Does that hold true? Right. So if you take any number which is A less than equal to B cube, for example, if you take minus 1 is less than equal to, let's say, 2 cube, and you, let's say, take 2 is less than equal to 3 cube, you will have minus 1 to be less than equal to 3 cube. And this will hold true in all cases in this relation. So every number which is less than a cube of another number or equal to the cube of another number, and if you have another number which is equal to the cube of another number, then the first number will always be less than equal to the cube of the other number. So this function, this relation is transitive. Great. Let's move to the next question. Okay, let's look at question number 6. Show that the relation R in the set 1, 2, 3. We have only 3 numbers in the set. Given by R, the relation 1, 2, 2, 1 is symmetric, but neither reflexive nor transitive. Right. So the usual drill. So we're going to write reflexive, symmetric, or transitive. Let's check. So what does reflexive mean? Every element needs to be related with itself, right? So in a set like 1, 2, 3, if you mean the relation needs to be such that every element is related with itself, that means we need to have a possibility of 1, 1, 2, 2, and 3, 3. This is where you can say that every element is related with itself, right? So you will have something like A, A. This is not the case in this, right? We don't have an A, A in this, so this is not reflexive. Correct? And is it symmetric? Is for every A, B, do you have a B, A? Yeah, you do have. In this set, you don't need to have a 3, 3, you just need to have a 1, 1 and 2, 2 because you don't have 3 in this relation as such, but that's the basic idea, right? So is it symmetric? Yes, for every A, B, you do have a B, A. So yes, this relation is symmetric. Is it transitive? So for an A, B and a B, C, do you have an A, C? You have 1, 1? No, you don't. So it's not transitive. And that's it. It's symmetric, but not transitive, not reflexive. Let's go to the next question. Show that the relation R in the set A of all the books in the library of a college given by R equals X, Y such that X and Y have same number of pages is an equivalence relation. Right. So relation R in the set A of all books in a library. So the set is all books in a library. So relation is X, Y such that X and Y have same pages. Same pages. Right. So for it to be a equivalence relation, what is the condition? You need to be reflexive. You need to be symmetric and transitive all together, right? So that's what we call, if it is reflexive, symmetric and transitive, it's called an equivalence relation. Correct? An equivalence relation has all 3 criteria satisfied, and that's exactly why we've been practicing all this, right? So that we can understand if a relation is equivalent or not. So now if we try to see if it is reflexive, so every element needs to be related with itself. That means a book X should have the same number of pages as itself. Obviously it'll have, right? So a book X will always have the same number of pages as X, right? So that's obviously true. You cannot have a book which is not the same as itself in the number of pages, right? So X, X holds true. So it is reflexive. So reflexive is correct. Now, is it true? Is it symmetric? So if X and Y have the same number of pages, will Y and X have the same number of pages? Of course, right? So it's basically saying the same thing in a different way, right? So it is symmetric. So is it transitive? If X and Y have the same number of pages and Y and Z have the same number of pages, will X and Z have the same number of pages? Obviously, they will. All of them will have the same number of pages. So it is transitive. So it is an equivalence relation. It is reflexive, symmetric, and transitive at the same time. So this set is an equivalence relation. Let's look at question number 8. Show that the relation R in the set A equals 1, 2, 3, 4, 5 given by R equals A comma B such that mod of A minus B is even is an equivalence relation. Show that all the elements of 1, 3, 5 are related to each other and all the elements of 2, 4 are related to each other, but no element of 1, 3, 5 is related to any element of 2, 4. Okay. So in the set 1, 2, 3, 4, 5, we want to show that this relation is an equivalence relation, right? So we want to show it is reflexive, symmetric, and transient at the same time. Correct? So is it reflexive? So if a comma b, if a minus b is even, will a minus a be even? Yes, it will be, because a minus a, will a minus a be even? Yes, a minus a is always 0. So 0 is an even number. A slip of the tongue, 2 times 0 is 0 and 2 times 1 is 2. So it is a multiple of 2, right? So 0 is an even number. So this holds true. It is a reflexive. Any number subtracted with itself will always be even, right? So this is a reflexive set. So this is a reflexive relation. Is it symmetric? So if a minus b is even, if a minus b is even, will b minus a be even? Yes, it will be. We have learned this in our one of the previous chapters. If you have if a minus b is even, that means either both are even or both are odd, right? Either both are even or both are odd. If you swap the places, you'll still have the same value. And the thing is, if you have a modulus sign, the overall value is always going to be the same, right? So either a minus b or b minus c, the value is always going to be the same. So that's also another way you can understand that a minus b and b minus a, and flip together and you have a modulus sign, you basically have the same value. So they are actually equal to each other. So if one is even, the other will obviously be even, right? So it is symmetric as well. Is it transitive? So if a minus b is even and b minus c is even, will a minus c be even? Yes, because if a minus b is even, you know that either a and b both are even or both are odd. If b minus c is even, you know that a and b are both are even or both are odd. So if a minus b is even and b minus c is even at the same time, so it has to be at the same time, correct? So if it is at the same time, that means a minus b, if both are odd, b will have to be odd and c will have to be odd. If a minus b, if a is even, b is even, b is even here as well, and c is also should be even here for it to entire thing to be even, right? So that means a and c will both be even or both be odd at the same time. So that means this also works as the right transitive relation. So if it is reflexive as well as symmetric as well as transient, it is an equivalence relation. It is an equivalence relation. So that's how you can prove that. Now, the second thing we need to show that all the elements of 1, 3, 5 are related to each other and that all elements of 2, 4 are related to each other, but no element of 1, 3, 5 is related to any element of 2, 4. Right. So this comes down to our understanding of what makes something even, right? So if A and B have to be even, then only elements of 1, 3, 5 can work, right? Will not be, they only the numbers which are all odd or all even will be able to make an even number when subtracted, right? So that's what I was talking about all this while. So if you have A as 1, you need to have B as either 3 or a 5 and C as a 3 or a 5, right? If you have A as 2, you will always need to have B as 4 or C as 4. You cannot have one even and one odd. So you need to know this, right? You need to know this fact that even minus even is always even. Odd minus odd is always even. Odd minus even is always odd, or even minus odd is always odd. It's basically the same thing. So if you have a modulus, you'll always have the right positive sign. So if you, in case you have, when you have a modulus, you have even minus even is always even and odd minus odd is always odd. So the only way a minus b modulus even is either everything is even or everything is odd. So only the elements of 1, 3, 5 can be together for this to work, or the elements of 2, 4 can be together for this to work. And that's the reason why you cannot have 1, 3, 5 and 2, 4 mixed together for this to work. Let's go to the next question. Show that each of the relation R in the set A equals x belongs to set of integers such that 0 less than equal to x less than equal to 12. So the set A is x belongs to set of integers such that 0 less than equal to x less than equal to 12 is given by, for one, R, the relation A comma B. The relation is A comma B such that mod of A minus B is a multiple of 4. Right? And second is R equals A comma B such that A equals B is an equivalence relation. Find the set of all elements related to 1 in each case. Okay, so for the first question, let's take the first question. This is the first question, right? So we need to find whether it is equivalent. So that means reflexive, symmetric, and transitive, right? So let's go with first question. So let's take the first question. So reflexive, symmetric, and transitive for the first relation, right? And this is the set. The set is set of all integers between 0 and 12, right? So if you see whether it's reflexive, if A minus B is a multiple of 4, will A minus A be a multiple of 4? A minus A will always be a multiple of 4, right? So A minus A modulus will be 0. And that will always be a multiple of 4. So it is reflexive. It's reflexive. Is it symmetric? If A minus B is a multiple of 4, will B minus A be a multiple of 4? Obviously. Since this is a modulus sign, this placement of the elements and the negative sign does not really matter. Whether you have B minus or A minus B, end of the day, the value is going to be the same. So if A minus B is a multiple of 4, B minus A will be a multiple. So these are basically equal. So this also is symmetric. Great. Now let's see whether if it is transitive, right? So if A minus B is a multiple of 4, and if B minus C is a multiple of 4, will A minus C be a multiple of 4? Now, there's an interesting way you can do this, right? So if A minus B is a multiple of 4, then you can say mod A minus B is 4x, right? If B minus C is a multiple of 4, you can say mod B minus C is equal to 4y, because it's a multiple of 4 and you have some factor next to it, correct? So now what we can do is, you can write this instead of this as, you can say this is equal to saying A minus B is either plus or minus 4x. So we don't know what the actual value of A minus B is, right? A minus B, A could be greater. If A is greater, this will be a positive value. If A is less than B, this will be a negative value. But the overall value will be the same, right? So in subtraction, if you have 5 minus 4, 4 minus 5 is also 1. 4 minus 5 is minus 1. 5 minus 4 is 1. The value is the same, right? The signs are different. So a subtraction will always give you, if you don't know which one is the bigger one, if you let's say plus 5 or minus 4 and minus 5 and plus 4, you will get either minus 1 or plus 1. Only two possibilities in any subtraction, right? If you don't know which one is the higher value. So if you don't know which one it is, you can always write it as, let's put both values. So let's say, for example, this also you can write it as plus or minus 4y, correct? Now if you add these together, you will say A minus B plus B minus C. This is cancelled, and A minus C is equal to plus or minus 4x plus or minus 4y. Now, one thing is very clear, right? Whether if you put it a mod here, let's say you put a mod here, you may not know what the exact value is, but you can know for sure that this is always going to be a multiple of 4, right? So it's always going to be something into 4x, some negative value, something into 4y, some negative or positive value, we don't know. But overall thing is always going to be a multiple of 4, that is for sure. What the exact value is, we don't know. So that means it is transitive, right? So both A minus B, B minus C and A minus C will be a multiple of 4. So this is an equivalence relation. This proves that it's an equivalence relation. Both R, S, T are true, which means equivalent. It is an equivalence relation. Okay, let's see the second one. So the second one says R equals A comma B such that A is equal to B. That's simpler. So what do we do? R S T. Is it is it true that A equals A? Obviously, A is always equal to A. As reflexive relation means an element will be related with itself, right? So A is equal to A, obviously true. Is it symmetric? If A equals B, will B equals A? Obviously, right? It is symmetric. Is it transitive? If A equals B and B equals C, will A equals C? Obviously, true. It is transitive as well. So it is also an equivalence relation. So it is RST true. It is an equivalence relation equal to E. Right. Now, second part, find the set of all elements related to 1 in each case. Now, in the first case, if you take the first case, we need to find the set of elements related to 1 in each case. So if A is 1, you need to find a set basically. So the set of all elements related to 1. So if you have 1 as one of the elements, which all could be related to 1, if 1 is here, you would need the other number to be 5, right? So if it has to be a multiple of 4, you need it to be plus 4, right? So 1 comma 5, and the next one would be 9, right? 1 minus 9, 1 minus 8, 1 minus 9 is 8, minus 8 basically, but mod is 8. So it'll be in multiples of 4. So it'll be 1 plus 4 plus 4 plus 4 and plus 4 and so on, right? So 13 and 17 and so on. That's how the numbers will go for this for the first set is equal to this. And the second one, for the set of 1, what would you get? The set would be, if you have 1 as one number, A is equal to B. It's just going to be 1 1 1 1 1. That's it, right? That's all it will be. Like if A equals B, what else would be the answer? It's just 1. So basically, it's a set of 1. That's it. Awesome. Let's continue then. For the question 10, we have give an example of a relation which is symmetric but neither reflexive nor transitive. Okay, so these are pretty tough to come up with if you get such a question in an exam. So ideally, you would have to remember a few examples for each of these types, right? So that's the only way you find it really, really hard for you to come up with something which fits all these criteria. So one example of this would be a relation of all inverse relationship of all inverses on a set of all non-zero rational numbers. So a relation of all inverses on a set of all non-zero rational numbers. Let's say, for example, a comma b, such that a is inverse of b, and on the set a is inverse of b. So the relation is a comma b such that a is inverse of b on set of all non-zero rational numbers. Now let's check, is it reflexive, is it symmetric, is it transitive, which is always what we do, right? So is it reflexive? Is a inverse of itself? No, right? A is not inverse of itself, not an inverse of itself. It can't be, right? So this is not reflexive. At least not all A's are, right? Not all A's will be an inverse of themselves, right? And is it symmetric? If A is inverse of B, does it mean if A is inverse of B, does it mean B is inverse of A? Yes, it is symmetric. So if you reverse A and you get B, if you reverse B, you would get A. So it is symmetric. Is it transitive? If A is inverse of B and B is inverse of C, does it mean A is inverse of C? No, not really, right? So it is not transitive. So this is a relation which is symmetric, not reflexive, and not transitive. It's really tough to come up with, by the way, so we'll have to remember this one. Now coming to the second one. So it has to be transitive but neither reflexive nor symmetric. Now R is a relation such that a person is an ancestor of another person. That's the literal relation you can create, right? So if somebody is an ancestor of somebody else, that what kind of relationship would that be? Would it be reflexive, symmetric, or transient, or any one of these? So for it to be reflexive, if A is an ancestor, and if there are two people A and B, and A is an ancestor of B, right? That's the relation we're talking about, right? Will A be an ancestor of themselves? No, A cannot be an ancestor of themselves. So the relation cannot be reflexive. Every element will not have a relationship with itself, right? So it will not be reflexive. A cannot be an ancestor of themselves. If A is an ancestor of B, will B be an ancestor of A? No, it's not possible, right? So if we have a grandfather and a father and a son, you cannot have the father become the father of the grandfather, right? So that's not going to work like that. Is it transitive? If A is an ancestor of B and B is an ancestor of C, will A be an ancestor of C? Yes. So if A is a grandfather and B is a father, and B is a father and C is a son, then A will be an ancestor of C as a grandfather and a son relationship. So this is a transient. This is a transitive relation. Great. Let's try question number 4. Reflexive and transitive, but not symmetric. So this relation where A comma B such that A is less than equal to B on a set of real numbers. Let's check. Is it reflexive, symmetric, and transitive? Is it reflexive? If A is less than equal to B, will A be less than equal to A? Obviously, right? It is reflexive. That's true. Will it be symmetric? If A is less than equal to B, will B be less than equal to A? No. In the case of equality, it will be, but if A is less than B, it will not. B will not be less than A, right? Only one is possible, so it is not symmetric. It's not symmetric. Is it transient? If A is less than equal to B and B is less than equal to C, is A less than equal to C? Yes, always. If it is equal, it's obviously true. If A equals B, B equals C, obviously A equals C. But if A is less than B and B is less than C, obviously, right? So if A is less than B and B is less than C, A has to be less than C. It always holds true. So it is transitive. So it is reflexive, not symmetric, and transitive. Let's go to the last question. Okay, for this one, let's see. If R equals A comma B, B comma C, A comma C, C comma A, and C comma B, and B comma A. Let's test this. Is it reflexive, symmetric, and transitive? So reflexive means for every element you need to have a relationship with itself, right? So we need to have A comma A, which is not there, B comma B is not there, C comma C is not there. So this is not reflexive. Is it symmetric? For every element you have the reverse. A comma B you have B comma A, right? B comma C you have C comma B. A comma C you have C comma A. Perfect. So this is symmetric. Is it transitive? Which means for A comma B true and B comma C you need to have an A comma C, right? And every other possibility. For B comma A and an A comma C you need to have a B comma C, right? And it is true, and that is transitive as well. So this is not reflexive but symmetric and transitive. Great. Now let's look at question number 11. Show that the relation R in the set A of points in the plane given by R equals P comma Q. Distance of the point P from the origin is same as the distance of the point Q from the origin. Okay. Is an equivalence relation. Further show that the set of all points related to a point P not equal to 0, 0 is a circle passing through P with origin as a center. Okay. So first we need to show that the relation P comma Q such that distance of P and distance of Q from the origin is the same, right? So distance of P is equal to distance of Q from the origin. Right, so let's get back to our drill. So is it RST? Right, so first, if the distance of P from the origin, will it be the same as the distance of P from the origin? Obviously, right? So distance of P from the origin will always be the same as distance of P from the origin. So it will always be the same value, right? So this is reflexive. Is it symmetric? If the distance of P from the origin is equal to distance of Q from the origin, will distance of Q from the origin be equal to distance of P from the origin? Obviously, right? This will be the same. So this will be symmetric as well. If the distance of P from the origin is equal to distance of Q from the origin, and if distance of Q from the origin is equal to distance of R from the origin, will distance of P be equal to distance of R? Obviously it will be, right? So transitive as well. So it is an equivalence relation. It is an equivalence relation. Cool. So now we need to show that the set of all the points related to a point P, which is not zero, is the circle passing through P with origin as the center. So what they're saying is, for all the points which are set here are basically, if P is not zero, this is not P is not the origin. Basically, P is somewhere over here, is a set of all points related to a point P such that the circle is passing through P and origin is at center. So basically, it's a circle like this. Right? And all these points are the points of this set, which is obviously true, right? So if you have a point Q, which is the same as the distance of point, if it's a point P, the distance is A. If another point is the same distance as A, another point is the same distance as A, every point here in this set is at the same distance from the origin as P, right? So if the distance of P from the origin is A, every other point Q and R and S and T, everything will be equal to A, right? And what happens when you have the same distance all around a particular point? So if you start from origin and if you draw lines, equal lines all in all the directions, it's called the radius, right? So you have a radius and you keep rotating the radius all around, and then you get a circle, and of course P lies on that circle because it has the same radius, and that's how you get the circle passing through P with the origin at O, right? Let's go to the next question. Show that the relation R defined in the set A of all triangles as R equals T1, T2 is such that T1 is similar to T2 is equivalence relation. Consider three right angle triangles, T1 with sides 3, 4, 5, T2 with sides 5, 12, 13, and T3 with sides 6, 8, 10. Which triangles among T1, T2, T3 are related? Okay, so R is defined as in the set A of all triangles. So such that T1, T2 such that T1 is similar to T2. You can write similarity this way, right? T1 is similar to T2 on a set of all triangles. All triangles. Right. Now, is it an equivalence relation? So let's do our drill R, S, and T. So if T1 is related, if T is T1, will T1, sorry, will a triangle T1 be similar to itself? Will a triangle T1 be similar to itself? Obviously, right? Every triangle will be similar to itself. And this is obviously a reflexive relation. Now, if a triangle T1 is similar to triangle T2, will triangle T2 be similar to triangle T1? Symmetric, remember, symmetric means you will be able to interchange the two elements and you still end up with the relationship intact. Right? So if T1 is similar to T2, T2 will be similar to T1. It's basically going to work that way. That's how an equivalence, that's how similarity and a congruence work, right? So if one is similar to the other will be similar to the other in the reverse way as well. Now, is it transitive? If T1 is similar to T2 and if T2 is similar to T3, will T1 be similar to T3? Of course, right? So the way you create the similarities through SSS or SAS, some sort of a similarity, right? So use some sort of a similarity to prove the similarity. If you're able to prove the similarity of these two triangles and you're proving these two triangles, you will be able to prove it with these two triangles as well, and the relationship will hold true. So it is an equivalence relation. It is an equivalence relation. Okay. Now, if you consider three right triangles, so these are the three right triangles that have been given to us. So we have the first one, we have the right triangle, a right triangle, and another right triangle. So the first one has sides 3, 4, and 5. We have a 3, 4, and a 5. All these are right triangles, right? And the second one has sides 5, 12, and 13. Hypotenuse is always the biggest one, right? 5 square plus 12 square is 13 square. We're 169, right? So 6 square plus 8 square is 10 square, right? Which triangles among T1, T2, T3 are related? Right. So basically, they are trying to. We need to prove that all these triangles are similar to each other, and that's how we can say that they are related. So is T1 similar to T2? Yes. So if you can see that T1, if you check T1 and T3, you can see that if these two are proportional to each other, right? So 3 into 2 is 6, 4 into 2 is 8, and 5 into 2 is 10. So clearly, by the SSS similarity, 3 by 6 equals 4 by 8. Right, so we figured out that T1 is similar to T3, but is we figured out that T1 is similar to T3, right? So in this real case, we know that this triangle 3, 4, 5 is similar to the triangle 6, 8, 10 because the sides are proportional. 3, 2 is 6, 4, 2 is 8, and 5, 2 is 10. So the sides are proportional to each other. But are these two triangles similar to each other? Is T1 similar to T2? Very simply, it's not, because 4 into 3 is 12, but is 3 into 3 5? No, obviously not. So 3 by 5 is not equal to 4 by 12. So since the sides are not proportional to each other, this triangle is not symmetric to T1. And if T1 is not similar to if T2 is not similar to T1, it's not similar to T3 as well. So these are not similar to T2. Only T1 is similar to T3. And that's what we have. Let's go to the next question. Show that the relation R defined in a set of A of all polygons, as R is P1 comma P2, such that P1 and P2 have the same number of sides, same number of sides. Awesome. Sorry. The same number of sides is an equivalence relation. What is the set of all elements in A related to the right angle triangle T with sides 3, 4, and 5? Great. Let's see. We'll get back to our usual drill. What's our usual drill? Reflexive, symmetric, transitive. Right. So if it has to be reflexive, so P1 should have the same number of sides as P1, right? Every polygon will have the same number of sides as itself. So obviously, it will be reflexive. Every polygon will have the same number of sides as itself. That's all we need for it to be reflexive, right? Now, is it symmetric? If P1 and P2 have the same number of sides, will P2 and P1 have the same number of sides? Obviously, just changing the two, but number of sides remain the same. So it is symmetric. Is it transitive? If P1 and P2 have the same number of sides, will P2 and if P2 and P3 have the same, if P1 and P2 have same number of sides, P2 and P3 have same number of sides, will P1 and P3 have same number of sides? Obviously, will also have the same number of sides. So it is also transitive. So it is an equivalence relation. Equivalence relation. Great. It is reflexive, symmetric, as well as transitive. Awesome. So the next part is, what is the set of all elements in A related to the right angle triangle T with sides 3, 4, and 5? So what is the set? They're asking what is the set of all elements in A related to the right angle triangle T with 3, 4, 5. So this is a right angle triangle T with sides 3, 4, and 5. It's a right angle triangle. Now, what is this set about? It's about having the same number of sides. Now, every single triangle will have 3 sides, no matter the angles, right? All triangles have always, whether it's scalene triangle, whether it's an equilateral triangle, whether it's an isosceles triangle, whether it's whatever other triangle you can think of, it's always going to be having 3 sides. In fact, the definition of the name given to a shape which has 3 sides is a triangle. It has 3 angles and by also 3 sides. So the set of all elements in A related to right angle triangle T is a set of all triangles. Is a set of all triangles. That is the answer. The set of all triangles. Cool. Let's go to the next question. Okay. Let L be the set of all lines in xy plane, and let L be the set of all lines in xy plane, and R be the relation in L defined as R equals L1 comma L2 such that L1 is parallel to L2. This is the way you write parallel, right, in math. Show that R is an equivalence relation. Find the set of all lines related to the line y equals 2x plus 4. Show that R is an equivalence relation. Great. Again, let's go back to our drill: reflexive, symmetric, transitive. So what is reflexive? If will L1 be always parallel to its own self? Yeah, by definition is the same line, so it's always going to be parallel to itself. So L1 is always parallel to itself. So it is a reflexive relation. Will if L1 is parallel to L2, will L1 be parallel to L1? Yes, of course. If L1 is parallel to L2, will L2 be parallel to L1? Yes, obviously. Literally just switching the names, right? So it's still going to be the same lines. If L1 is parallel to L2 and L2 is parallel to L3, will L1 be parallel to L3? Of course. If you have a line L1 and you have a line L2, and if you have a line L3, right? So L1 is parallel to L2 is parallel to L3. So if these two are parallel, and these two are parallel, obviously these two will be parallel. So this also holds true. So this is an equivalence relation. This is an equivalence relation, right? Show that R is an equivalence relation. It is an equivalence relation. Find the set of all lines related to the line y equals 2x plus 4. Now, when you have a line which is 2x plus 4 and you want to find all the lines which are parallel to this line, that means the slope is the same. You need to just keep the slope constant and vary everything else, right? So when you have a line like y equals 2x plus 4, first let's plot the line. It will be easier for you to visualize how you can make that work. So first of all, if you put x equals 0, you get y equals 4, right? So 0 comma 4. So this is the positive y axis, this is the positive x axis. So 0 comma 0 is here, right? 0 comma 4 will be 1 2 3 4, let's say it's over here. So this is 0 comma 4. And if you put y equals 0, you get x equals minus 2, right? So y equals 0, minus 4 goes here, x equals minus 2. So that means this is minus 2 comma 0. So the line moves like this. The line would be something like this, right? Y equals 2x plus 4 would be something like this, right? Now, if that is the case, all the lines which are parallel would be somewhat shifted. You just need to shift this line slightly this way, slightly like this. And what is this line? So there's going to be one line which is going to go through this, right? So there's going to be one line which goes through the origin. Now, what is that line? Now, this line is nothing but this intercept going to 0. See, this is the intercept. The intercept is 0 comma 4, right? So if intercept goes to 0, it means this line gets shifted this way, right? That's all this is. So the actual line is important is y equals 2x. Y equals 2x is the line which goes to the origin, and everything else is just shifted by this amount. Whatever amount is shifted here, it's just shifted that way. So it's shifted this way by 1, shifted by 2, or whatever, 1 minus 1, 1, 2, 3, anything. So any line which is going to be parallel to that will always have the form y equals 2x plus c. So c is the constant, c is the y-intercept, right? So any line which is going to be parallel to a line of this nature, you just need to keep this term constant and just vary this term, and that will give you all the lines which are parallel to that line. Great. Let's go to the next question. Let R be the relation in the set 1, 2, 3, 4 given by R equals 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, 2, 3, 3, and 3, 2. Choose the correct answer. R is reflexive and symmetric but not transitive. Awesome. So let's just check, right? We just need to check. Reflexive, symmetric, transitive. That's all we need to check. And this time we're going to do it for a specific given relation already given to us. We don't have to worry about thinking about what it is, and actually just look at the set and the relation. Now, is it reflexive? Does every element have its own relation? That's the first check, right? Yes. So for 1 we have 1 comma 1. Yes, that works. For 2 we have 2 comma 2. Yes. For 3 we have 3 comma 3. Yes. For 4 we have 4 comma 4. Yes. So it is reflexive. Every element is related to itself. So it is reflexive. It is reflexive. Is it symmetric? Is it symmetric? Is it symmetric? Does every pair of element have the opposite pair? Does every pair have an opposite pair? So for 1 comma 1 and 2, we don't have to worry about these elements. These elements are not counted while we're looking at the symmetric property, right? So we just need to see the couple pair of elements. So for 1 comma 2 we need 2 comma 1, we don't have it. 1 comma 2 comma 1 does not exist. For 1 comma 3 3 comma 1 does not exist. Even 1 is enough, but anyway, I'm just looking at 3 comma 1 does not exist. So it is not symmetric. It is not symmetric. Is it transitive? So for 1 comma 2 and a 1 comma 3, do we have a 3 1 comma 3? No, we don't have it. So 1 comma 2 we have a we don't have 2 comma 3, so we can't really take that example. But for 1 comma 3 and 3 comma 2 we need a 1 comma 2. Oh yeah, for 1 comma 3 and a 3 comma 2 we have a 1 comma 2. That seems to work. For 3 comma 2 we don't have a 2 comma 3. Okay, yeah, it looks like it's transitive. Okay, it is transitive. I can give you that. So you can only take the elements such that if 1 comma 2 is there, you need to have something like a 2 comma 1 for you to be even able to come up with the transitive property, right? So you can't just take 1 comma 2 and come up with the transitive. You can't make up the second part of it. So you need to finish the transitivity, right? So 1 comma 2 is there, 3 comma 2 is there. So 1 comma 2 is also available. So it is transitive. It is reflexive and transitive but not symmetric. Answer B is the answer. Great. Let's go to the last question of this exercise. Let the relation R in the set N given by R equals A comma B such that A equals B minus 2 and B is greater than 6. Choose the correct answer. 2 comma 4 belongs to relation R. 3 comma 8 belongs to relation R. 6 comma 8 belongs to relation R. 8 comma 7 belongs to relation R. Okay. So relation is such that A equals B minus 2 and B is greater than 6. Great. And they have not told anything else about it. It's a set of n, right? So if A equals B minus 2 and B is greater than 6, then let's take B as 7, 8, 9, 10, 11, and 12. So if B is 7, A would be, if B is 7, A would be 5, right? If B is 8, 8 minus 2 is 6. So this would be 5, 6, 7, 8, 9, and 10. So these are the pairs we have. We can have 5 comma 7, we can have 6 comma 8, we can have 7 comma 9, we can have an 8 comma 10, we can have a 9 comma 11, we can have a 10 comma 12. Are any of these part of this? B has to be greater than 6. So this is not possible. 8 comma 7 is not possible. A has to be less than B. 6 comma 8 is the answer, right? Yes, 6 comma 8 is the answer. It's answer C. Okay, I'll see you in the next exercise. Have a nice day.